Hello everyone. Cardiac muscle is something that we have learned throughout our entire lives, starting from, grade 6, in fact, is the first time I was taught about the various nuances of the cardiac musculature. So today, as a second year medical student, I'm pretty sure I know a lot more than what sixth grade me knew, but it is a core, if you think about it that way. It's the core of your understanding of the cardiac contraction. My other videos are pretty much incomplete if I don't talk about the basic properties of the cardiac musculature. This video is not just for medical students, but even for a little over enthusiastic uh, 10th grade, 11th grade students who want to know just that little bit more about the nuances of the cardiac musculature. This video is for those people. So today I'm just going to start with, I've prepared some light topics about the property, so we'll get into it right away. Okay, so as you can see here, we have the properties of the cardiac muscle. So first of all, let's go through some terms. As we all know, a medical presentation is incomplete if you don't hear about terms that you don't understand. So I'm going to try to make your lives a little bit easier here. Bathmotropy. Bathmotropy, like if you think about it, it's not about taking a bath, but nah, bathmotropy is about the excitability of the heart. So a positively bathmotropic stimulus would mean anything that's increasing the excitability of the heart. And the negatively bathmotropic stimulus is just vice versa. So bathmotropy, it can normally in electrical impulses, if we send an impulse to the heart, a lot of times it is bathmotropic. It's going to increase the overall excitability of the heart. So that's just a term. Inotropy is the contractility of the heart. So again, like a positively inotropic agent would increase the contractility while a negative one would decrease it, right? Now, the Starling law, also known as the Frank-Starling law. Now, I've had a lot of students complain about this Frank Starling law, like most of my friends, they don't really understand it. So I'm going to try to explain it in a very simple way. The heart, when the ventricles of the heart are going to contract, they're going to send most of the blood through to the systemic and pulmonary circulation. The force of contraction is dependent on a lot of things. So the Frank Starling law, particularly, will depend states that the force of contraction of the ventricles depends directly, that is directly proportional to the end diastolic volume that it of the ventricles. That is, after the diastole is over, whatever is the volume of blood, which is the maximum volume of blood that is going to be present in the ventricles. If that's more, then the force of contraction will be more. But within physiological limits is a key statement that we miss and we don't write it down, but it's really important. And I'm going to explain why. So, what happens? Why am I staying within physiological limits? Well, the basic reason is that when you put more than the physiological limit of blood in there, the muscle is going to start tearing. If a muscle tears, if you pull the muscle so much that it tears, there is no way that the force of contraction is going to increase. So a lot of times a question will be posed to you where it will ask about the Frank-Starling law, but it will say that the blood is outside of the physiological limit. Then the answer changes, right? The force of contraction decreases. Yes. Now we go to the syncytium. Syncytium basically means a mesh of cardiac muscles, where if one cardiac muscle fiber contracts, then all of them contract. Why? Because they're all connected to each other. We'll go into that in a little bit, but that's basically what syncytium means. Now I've written types. Now, syncytium doesn't really have types. It's just in the heart there are two syncytia, uh, the atrial syncytium and the ventricular syncytium. They are independent of each other, right? And the way that both of them are, beating simultaneously is a testament of the special excitatory stuff that's in the heart, which we covered in the first video on this channel. So that's just the SA node, AV node, the Purkinje fibers. If you want, check that video out. Pretty good video. I hope. But yes, cardiac musculature, again, this is atrial muscles, ventricular muscles, and special excitatory muscles. Now we come to the anatomical characteristics. Now the anatomical characteristics is that the cardiac meshwork of fibers is of a lattice-like arrangement. A lattice arrangement is kind of like this, it will keep interweaving over each other, right? The whole reason for this interweave is because when the cardiac muscle is developing, it develops in a spiral, right? So in a spiral, a lot of time they'll get molded into a lattice like framework, which is why embryology is a great subject and it's very interesting. You guys should read it. It's great. So, it's very pretty how the heart will automatically go into this lattice arrangement. Well, I think it's pretty. Now we look at the striations. Striations pretty simple. Your standard actin myosin uh, fibers in the contractile proteins and the myofibril, right? Standard stuff. Gap junction. Basically, gap junctions are special membranous structures that are going to cause the movement of ions to be very fast, which is the reason that these gap junctions are found in the intercalated disc. Intercalated discs are one of the key features of cardiac musculature where you'll see these little discs everywhere in the middle of the striations. So these intercalated discs basically have gap junctions, right? Now let's look at the physiological characteristics, what we are really interested in. Excitability. Now, when we talked about bathmotropy, one of the main features is that the cardiac muscle is auto-excitable. It gets excited by itself, and you know, and it can even get excited when I send an impulse through it. That's basically what excitability is all about. It's bathmotropy, basically. Autorhythmicity. Autorhythmicity again is because of the sinus fibers. The sinus fibers fire at a certain rate, which is why they control the majority portion of the electrical conducting system. Again, I talked about this in the other video, but that's basically it. The sinus fibers are auto-excitable because of the leaky sodium channels, the pacemaker cells, and everything. So that's basically it for autorhythmicity. If we're talking about contractility, I mean, it should be fairly obvious that contractility is basically means that the cardiac muscles, they have the capability of contracting and sending enough blood, right? They're going to send that blood and they are capable of the contractions. The second contractility goes, I think the cardiac musculature kind of loses its whole point, because if it's not contracting, it's not going to be able to do anything, unfortunately. Now, let's talk about the electrical conduction. Electrical conduction, again, we talked about this, but all the cardiac myofibrils, they have the ability of electrical conduction through their systems, mainly because of the passage of ions, because again, we talked about the intercalated discs right here. So again, the intercalated discs, they'll allow for the rapid movement of ions, which is going to allow a current to pass through, which is great actually, because if the heart wasn't electrically conducive, then it wouldn't contract at the same time. There would be no physical way to make it contract in a specific rhythm. So that's great. Now, syncytium. We talked about syncytium already. We talked about the discs and we talked about the importance of the discs. So what you'll see is that when you're writing for the physiological characteristics, a lot of the times the answers will just come up straight, right? It's one of the after the other. You don't have to, think about it too much. Now we come into the more important ones, or kind of like not exactly important, but more relevant to me and medically relevant ones. The all or none law. All or none law, to the medical students out there, and even some 12th graders who will know this, is that when you when a muscle or a nerve fiber, whatever it is, it can only be excited if the stimulus that I'm giving the nerve fiber or muscle exceeds a threshold amount. Like, let's say the threshold is around 90, okay? If I give it 10, 20, 30, 40, it's not going to work. It's not going to fire. The second I give it 90 or even 100, even 200, it will fire at the same rate, right? Unless there's some changes, which we'll talk about later, maybe. But that's the all or none law. So the all or none law here is a little bit different. In the cardiac systems, they are a little bit different. They basically state if one muscle fiber is triggered, then the whole syncytium gets triggered because of the intercalated discs and how fast the ions will move across each other, which is the beauty of the heart. So the all or none law is active for the cardiac musculature. If I stimulate one fiber, then the whole heart will contract. Now, prolonged action potential. I think I can show you a diagram actually for this one. See this diagram right here. Okay, this is like the action potential curve. Well, not exactly action potential. This is force of contraction. But I can somehow relate the action potential with this because action potential is pretty simple. It's just like your normal curve, but the plateau phase is elongated, right? So you can kind of imagine this is how the contraction is taking place of the heart while I'm talking about the action potential, right? Now, what happens in the heart is that the refractory period, which is basically like the minimum amount of time between two nerve impulses, like if I nerve impulses that will cause a contraction in the heart. So if I give an impulse in the middle of a refractory period, the heart won't contract a second time. But what will happen is, that's why I told you to keep this in mind. In the relative refractory period, if I stimulate it a second time, it's going to contract, but it won't contract that much. Now, there's a lot of reasons for this. The reasons aren't really the cause for this video, but I'm going to tell you about them anyway. So what happens is that if I, in the refractory period, basically, it's like a recovery period. The heart is recovering. And if you give a premature contraction, that means you're giving a nerve impulse in the middle of a relative refractory period, then the heart hasn't recovered completely. The calcium ions are not flooding the heart again due to the decrease in calcium ions, due to the increased heat of the heart, due to the lack of beneficial effect. All these reasons will give you a subpar contraction, right? Which is why you can see the difference. And this is after the refractory period. I'm giving you this contraction. So notice how the heights are the same, but this premature one, it's quite low, right? So that was about the refractory period. Now, the normal skeletal one is, I think it's about 1 to 3, sometimes even 10 milliseconds. Different books will give you different values. Just whatever reference book you use, just go through that one and yeah, just memorize that value. But the cardiac one is pretty specific. Cardiac one, it has two different. If anyone asks you the question, the answer is 0.15 seconds to 0.35 seconds. But I'll give you some extra information here that the atria will be around 0.15 seconds, but the ventricles surprisingly have 0.25 to 0.35 seconds of refractory period. So if I continuously stimulate the atria are going to get stimulated more frequently than the ventricles, which can sometimes be asked as a question. Now, calcium importance. Calcium importance is like, it's quite important in the understanding of your contraction. So I would really suggest that you go through the normal excitation contraction cycles in skeletal muscles and then come to this. But if you don't want to do that, I'm going to explain it to you. It's just you'll find it a little bit easier to understand. So now in the heart, there are these transverse tubules. There are transverse tubules which are going to have a lot of calcium ions stored in them. So now the sarcoplasm, there's a sarcoplasm in the heart in any muscle, and there's a sarcoplasmic reticulum. Sarcoplasmic reticulum contains the calcium ions. I'll show you a diagram to make it a little bit easier. This is the sarcoplasmic reticulum. This is the cytoplasm of the muscle, right? And this is just an action potential that has been triggered, right? So now the action potential got triggered. Yeah, it goes. It goes through the calcium channel. It goes through the calcium channel, basic stuff. Now, if the calcium channel got activated, calcium floods into the cytoplasm. And now, what will happen is that the calcium is going to actually open the ryanodine receptors in the sarcoplasmic reticulum, and it will open an additional calcium container. You can think of it as like a big container. Just a little bit of calcium comes, opens it, and the whole container full of calcium will fall down. All this calcium comes out, there's a calcium signal, and this will cause the contraction of the fibers, which is the excitation contraction cycle. The actin myosin will contract because of calcium. That's a different story. But this is essentially how contraction will work. Now, for relaxation. If relaxation, sarcoplasm will use an ATP transport transport protein to get the calcium in. So calcium that was given out is getting pumped right back into the sarcoplasmic reticulum. Also, the calcium is going to go out and it's going to let the sodium come in, which will actually help in the sodium potassium ATPase pump. You know, sodium potassium ATPase pump is quite important to maintain the cytoplasmic stability of ions. So this is how that works because of this calcium sodium pump, right? So this was the relaxation, and this entire thing, by the way, is the T tubules, right? This is just the T tubules. Uh, Other than that, uh, okay, yeah. So I almost forgot, but the thing is that the T tubules of cardiac musculature is different from the T tubules of skeletal musculature. Cardiac musculature, think of it as a cylinder, right? If my maths is not wrong, it's been a while since I've done math, but the volume of a cylinder is pi r square h, right? Well, r being the radius and h being the height of the cylinder. So you can kind of use that thing. So I'll give you this that T tubules have 5 times the diameter or the radius. It makes the same sense. 5 times the radius of the skeletal muscle T tubules, right? The good thing about it is that if you think about it, then it's 5 squared, so it's 25. So T tubules have 25 times the volume of a skeletal T tubule. So T tubules are very important in cardiac musculature. It's just, if someone asks you why are T tubules important, why is it important, why do we need it? This is the reason, because it's very dominant. Then again, if we come to the Frank-Starling law, we explained it there itself that Frank-Starling is the end diastolic volume, but within physiological limits. Now let's talk about fatigue. Fatigue, the heart doesn't get fatigued. Like if you got fatigued in, your heart just suddenly got fatigued in the middle of the night or something, then yeah, it's bad news. You're basically dead. So the beautiful reason why the heart doesn't get fatigued is because of the refractory period. It's a very long refractory period, which I'm not sure if I mentioned the reason, but the long refractory period is because of the calcium ions that are coming inwards, right? If the calcium ions keep coming inwards, then the repolarization cannot take place. That's why it's still like depolarized. Once they come inwards, then the repolarization can take place and the regular action potential stuff can take place. So because of the inward movement of the calcium ions, it has a very long refractory period, right? Uh, so because of that, so You remember how I talked about if I give it prematurely, then the heart isn't completely rested yet. But because of the long refractory period, the heart is going to be rested if you give it after the refractory period. Blood supply, the heart is supplied by the coronary arteries, the left and the right, left coronary artery with the anterior descending and circumflex, and right coronary arteries there. That's basic stuff. That's more of an anatomy thing. But the basic thing you need to know is that the coronary arteries are going to keep the heart very well supplied with blood. So any metabolites that are created in the cardiac musculature will be removed quite quickly so that it doesn't cause any kind of fatigue. Now, the cardiac uh, the cardiac musculature is completely aerobic. Anaerobic respiration does not take place there. So, which is great because yes, aerobic takes a lot more energy, but it gives a lot more energy too, and it doesn't create the harmful waste products like lactic acid, which it will do in the limbs, which is why you get tired and everything. It has a lot of mitochondria, which is obvious because if it's aerobic, then it has to have a lot of mitochondria to sustain that kind of you know oxygen. So this is basically it about the properties. If you write these stuff and if you understand them, I think you'll be very easily you'll be very capable in understanding the future videos. And yeah, that's basically it for today. I hope you guys had a good time. I definitely did. Uh, Unfortunately, I have to attend a class after this immediately. I think I'm missing part of it to make this video, but the it's rather fun doing this. So thank you so much for your time.